Bismillahirrahmanirrahim. Okay, now let us see the exercise on power budget. So before we proceed with the exercise, I would like to refresh back on how to do the conversion of watt to dB to dBm. Okay, so basically, if you want to convert from watt to dB, you need to log the value. So 1 watt equal to 10 log 1, and you will get 0 dB. So if you want to convert watt into dBm, so 1 watt equal to 10 log 1 divided by 1 milli. 1 milli is 10 to the power of negative 3 equal to 30 dBm. So 1 watt equal to 30 dBm. So we can conclude that 1 watt equal to 0 dB equal to 30 dBm. So from here, actually, you can convert from dB to dBm straight away. Okay, so if you want to convert from dB to dBm, you just need to plus 30. Okay, from dBm to dB, you need to minus 30. Okay, for example, if you want to convert from 10 dB to dBm, just plus 30. So plus 30, you will get 10 plus 30 is 40 dBm. Okay, from 5 dBm to dB, just minus 30 and you will get negative 25 dBm. Okay, now let us look on the first example of power budget calculation. So before we proceed, I would like to remind you that when you do calculation, you should remember some of these rules. Okay, so if you are adding or subtracting dB with dB, okay, dB plus or minus dB, you will still get the result in dB. Okay, so dB plus or minus dB, the result is dB. dBm minus dBm, your result will be dB. Okay, dBm plus or minus dB, you will get dBm. Okay, so for me, I always like to remember the first one. Okay, in case you forgot these two, just remember no matter you add or subtract dB, you will still get dB. Okay, but if you can remember these two, it is better. Okay, dBm minus dBm equal to dB, dBm plus or minus dB equal to dBm. Okay, so let's proceed. An optical link operates at 20 megabit per second and BER of 10 to the power of negative 3. Silicon pin photo detector. Okay, so this is our silicon pin photo detector, our photo detector. Operating at 850 nanometer is chosen. Gallium aluminum arsenide LED is chosen with an average optical power level of 50 microwatt. Okay, so 50 microwatt, if you convert into dBm, you will get negative 13 dBm. Okay, so this is our power transmit, 50 microwatt, which is then coupled to a fiber fly lead. Allowable power loss is 29 dB. Assume a 1 dB loss occurs when the fiber fly lead is connected to the cable, and another 1 dB connector loss occurs at the cable photodetector interface. The cable chosen is a multimode with attenuation alpha of 3.5 dB per kilometer. Including a 6 dB system margin, the possible transmission distance for a cable L can be calculated. Okay, so from the graph of receiver sensitivity versus the bit rate, we can actually determine what is our photo detector sensitivity. Okay, so from the graph, you can actually get the sensitivity, the receiver sensitivity is negative 42 dBm. Okay, so we have the formula that the total power loss or the allowed power loss is equal to power transmit minus power received, and it is equal to the total loss. Okay, so let's calculate the allowed power loss. We already know this 29 dB. So let's calculate power transmit minus power received. So our power transmit is 13 dBm. Our power received is the receiver sensitivity, which is negative 42 dBm. Okay, so if you calculate this dBm minus dBm, you will get dB. Okay, that's how you get 29 dB. And from here, we can see that power transmit minus power received is equal to the total loss or the allowed loss, the allowable loss, which is 29 dB. Okay, so this allowed loss or the total loss is equal to the all the losses that contribute to this link. Okay, the first one is 1 dB loss at the fiber fly link, and then another 1 dB connector loss, 6 dB system margins, and 3.5 L. This is actually the attenuation of the fiber. 3.5 times with L. So we get dB per kilometer, the unit. Okay, because we don't know the length yet. Okay, so we have to equate this equation with 9 dB. Okay, because this is the total loss equal to the allowable loss. Okay, so when you equate this, you can actually get what is your L, what is the link length. Okay, the length is equal to 6 kilometer. Okay, so let's see the graphical representation of our previous exercise. So at the beginning here, we have the power transmit, which is negative 13 dBm. Okay, so at first we have the power transmit negative 13 dBm. And then we have the loss due to the connector, which is 1 dB. After that, we have the fiber attenuation, okay, due to the multimode fiber attenuation, 3.5 dB times with the length. Our length is 6 kilometer. And then we have the system margin, okay, which is 6 dB. And finally, we have the connector loss. Okay, the connector loss at the receiver, which is 1 dB. And finally, we will reach our pin photodetector receiver sensitivity, or our power received, which is negative 42 dBm. Okay, so this is the comments from the link loss budget calculation. Okay, so previously we have seen that our receiver sensitivity is negative 42 dBm. Our power transmit, which is the LED, the power transmit is negative 13 dBm. We have 1 dB loss at the transmitter and at the receiver due to the connector loss. We have the safety margin of 6 dB, our tolerable loss of 21 dB, and finally, our maximum possible transmission path length L is 6 km. Okay, so our system cannot be more than 6 km. So, because this is actually the maximum distance length. Okay, so now let us look on another example on power budget calculation. Okay, so let's see the second example. Consider a 1550 nanometer laser diode that launches a 3 dBm optical power level into a fiber fly lead. Okay, so this is our power transmit, 3 dBm. And indium gallium arsenide APD. Okay, so this is our photodetector with negative 32 dBm sensitivity at 2.5 gigabit per second and 60 kilometer long optical cable with 0.3 dB per kilometer attenuation. Okay, so this is the fiber attenuation, 0.3 dB per kilometer. Assume that here, because of the way the equipment is arranged, a 5-meter optical jumper cable is needed at each end between the end of the transmission cable and the Sonnet equipment rack. Assume that each jumper cable introduces a loss of 3 dB. In addition, assume 1 dB connector loss occurs at each fiber joint, 2 at each end because of the jumper cables. Okay, so from this information, actually we can come out with this table. Okay, so this is our components, again, and this is our power. Okay, so our laser or our power transmit is 3 dBm. Okay, so this is the power transmit from the laser. Okay, our 1550 nanometer laser. Okay, our power transmit is 3 dBm. Our receiver sensitivity is negative 32 dBm. And then we have the source connector loss of 1 dB. Okay, at the source, we have the jumper plus the connector loss, which is 3 plus 1 dB, which is 4 dB. And then we have the cable attenuation. Okay, so we know that our link distance is 60 kilometer. Fiber attenuation is 0.3 dB per kilometer. Okay, to get the total fiber attenuation, we just multiply 60 kilometer with 0.3 dB per kilometer. Okay, so you will get 18 dB. Okay, and at the receiver, you have another jumper plus the connector loss, which is 3 plus 1 dB. And finally, the receiver connector loss, which is 1 dB. Okay, so here they calculate the power margin because we want to know what is our power margin. Okay, so previously I have shown to you what is our power margin. Okay, the formula is power transmit minus power received minus all the losses. Okay, so in order to ensure that our system is viable, our power margin must be greater than 0. Okay, so power transmit minus power received, or the receiver sensitivity, 3 minus negative 32 dBm, you will get 35 dB. Okay, so 35 dB minus 1 dB, you will get 34. 34 minus 4 dB, you will get 30 dB. 30 dB minus 18 dB, you will get 12 dB. 12 dB minus 4 dB, you will get 8 dB. 8 dB minus 1 dB, you will get 7 dB. Okay, so this is our final power margin. And from here, we can conclude that our system is viable because our power margin is greater than 0. Okay, because our power margin is equal to 7 dB. Okay, so again, this is still the same calculation as the previous one, except that in this table, they insert another safety margin of 6 dB. So previously, we have got our power margin of 7 dB. So if we include another safety margin of 6 dB, so 7 dB minus 6 dB, you will get 1 dB. So this is our final power margin. So again, our system is still viable. Okay, because 1 dB is greater than 0 dB. Okay, so our power margin is still greater than 0 dB and our system is still viable.